Okay, we're going to do sort of a full-fledged evaluation problem here. And we've got a beam up here. I'm only showing you half the beam, so I'm showing you a support over here. But I'm only dimensioning the beam from the face of support out to the center line. And I say that distance is like 11 feet, so the clear spacing between supports would be 22 feet. But, you know, if it's a uniformly loaded beam, a lot of people will only show you half the beam. This one is a uniformly loaded beam. It's got a factored load of 5 kips per foot. We'll say that that factored load includes everything. So it includes self-weight, it includes bed load, it's a factored load, it just includes everything. The stirrups that I'm showing the first stirrup starting 3 inches off the face of the support, and then I'm showing 18 spaces at 6 inches. That is really, that first one out there is really not a spacing, it's a location. All right? A lot of times when you take the stirrup spacing, especially the closest stirrup spacing, 6 inches, you always locate the first one at approximately half of whatever that initial stirrup spacing is. So you don't have to do that, but it's sort of common to see that. You know, if I had 6 inches as being my stirrup spacing, that my first one would be located 3 inches out from the support, or 2 inches out from the support, or 4 inches out from the support. And that's just sort of a rule of thumb. Okay? All right. The first thing we want to do here is we'd want to evaluate this. The biggest part of the evaluation is this. Is my design capacity greater than or equal to VU? I mean, that's really the heart and soul of evaluation. I mean, we can start looking at, you know, does the spacing meet this criteria, or the stirrups cut off in the right place? But that's really the big thing. Okay? So, in order to do that, the first thing I'm going to do is draw a shear diagram. Now, again, I'm only going to draw half of it because the other half looks like the same. So this is a uniformly loaded beam. I'm only drawing a shear diagram from the face on out because really it doesn't matter what happens over the support. So being 11 foot length, being 5 kips per foot, I'm going to have a maximum, I'm going to have a shear diagram that, you know, again, looks like so many of the shear diagrams that you've seen in the past. It's going to have a reaction there at the support, or at the face of support, of 55 kips. And it's going to go down to 0 in the middle of the beam. All right? The number 1 code-related item talks about the critical shear. And what they're saying is that I can really design for the shear, or evaluate in this case, for the shear at a distance d from the face. So my shear, they're going to allow me to evaluate for, at least in this region closest to support, is going to be that shear, whatever value this is, 20 inches out. All right? That's what the code says. The critical shear is a shear that occurs a distance d out from the face of support. Basically what they're doing is they're giving you a break. All right? They're saying, you know, we realize shear is bigger in here, but because of this big upward force that the column gives us, or the support gives us, you know, some of that's going to be negated. How are we going to find this point on this straight line? Somebody says straight line formula? Okay. I'm looking for a y value, VU critical, which is equal to the slope, m. What's the slope of my line here? Minus 5 kips per foot. Times an x value. What's mx? What's the x value here? 20 inches, but since it's 5 kips per foot, I'm going to change 20 inches into feet. Plus B, my y-intercept, where the line starts at. Where does the line start at? 55. So VU critical is simply just an application of the straight line formula. VU critical, in this case, comes out to be what? 46.6 kips. So basically, what the code is telling us is when you evaluate this or you design this beam, you can just sort of lop off this top portion because the maximum shear is the critical shear out here in this region closest to the support, and it's 46.6 kips. Okay? So again, my shear diagram really, as far as utilization of it, sort of looks like this now. All right. I've got 6-inch spacing across my whole beam. Phi Vn is phi times Vc plus Vs. Phi is 0.75, V sub c, 2 square root of 3,000, B is 14 inches, D is 20 inches. Calculate for me V sub c. What was it, please?
26,290.
26,290 pounds, or 26.3 kips. Somebody else get that?
30,000.
Yeah, I got 30,000 too.
30,000?
Yeah.
30,672.
Hang on.
30,600, yeah.
Okay, scratch that. 30,000,
Sorry.
672.
Yep.
So 30.7 kips. Are we good?
Yeah.
All right. You sure you use 3,000 under the square root, right?
Yep.
Okay. Okay, 30.7. Remember that. V sub s is AV. I'm using number 3 U-shaped stirrups, so that's 2 times 0.11. 60 KSI steel. D is 20. My spacing is 6. What's V sub s? 44 kips. All right. So phi is 0.75. V sub c was, what did you tell me? 30.7
Yeah.
plus 44 kips. Somebody tell me what phi Vn is equal to now. Say it again, please.
56.
56 kips. All right. What I'm about to do here is what they call the shear envelope. I've got my VU diagram. I got my shear diagram, basically. I've lopped off the top because of the critical shear. I'm now going to plot my phi Vn on there. So I come up here to 56 kips, and my phi Vn, my design capacity remains 56 kips as long as I got a 6-inch spacing. So I can look at this graphically. Hey, here's VU. Green line. Blue line is phi Vn. What does that tell me? Phi Vn is greater than VU. I like to see phi Vn above this line. It stays that way until what happens? Until you either change spacings or you end stirrups. And here, I'm ending stirrups. I'm going to drop. How far down would I drop? No, not to zero. You would drop down because you no longer have VS. You have no spacings in it, no stirrups. So you don't have a spacing. So V sub S becomes 0. So what would you have left here? Phi V sub C. Somebody calculate for me what phi V sub C is. What was it, please? 23 kips. So you go down to 23 kips here. Now, the code says I'm only allowed to do that when this value, VU, is less than or equal to phi VC divided by 2. So the code says, hey, you're not allowed to do that unless VU is less than, in this case, you're going to tell me 11.5 kips. So the code has a criteria that says, no, hang on, just being greater than your VU line isn't good enough. You got to be able to meet this. So the question becomes, what's that point right there? What's the value of that line, of the line at the point where I've cut stirrups off? How are we going to figure out what that value is? Well, I'd say it's a straight line again. It's a value, a y value basically. It's a VU value. Okay? VU is equal to, what's my slope of my line? -5. How far out x distance wise am I? Well, I'd say I'm 9.25 feet out. Okay? 18 times 6 inches sounds like 9 feet, and I got another 3 inches. So 9.25, and I started up here at 55. So what is VU at this point?
9.
Is it 9 kips? Is 9 kips less than or equal to 11.5? Yeah. All right, so I met that code criterion. I'm okay there. Okay? So I not only, when I'm spacing stirrups, I have that 6-inch spacing above VU, good. But where I decided to cut stirrups off is good also. Now, there's only one other thing that really you could check. And that is the 6th inch, is that, make sure that that's not over your maximum spacing. All right? So you got those 3 formulas to calculate, you could do that. We can say that for another day, because I can tell you right now, D divided by 2 is 10 inches. And I'm not over 10 inches, so even if those other formulas calculate it to be less than 10 inches, I'd still be, which they won't, those other 2 formulas. Minimum, typically what's going to control is D over 2, but you can calculate the other formulas. They probably end up to be 16 to 22 or something like that. So you can check that as well too. But for the largest part of it is that right there.